transition state correspond to that state may be the highest energy or may not be highest energy. That is the central point. So yesterday I also told that we will discuss various kind of techniques, that is the experimental techniques mostly, to determine the rate determining step or nature of the transition state at the rate determining step of a particular reaction. So the first thing is the order of reactions that you are quite familiarized from your high school and also in the Shashank Dev's class in the first half of our lecture of this course. So just recapitulations with a little bit of couple of examples that you know that the zero order reaction, right? So I'll go fast a little bit. So the rate is independent on the concentration of the reactant, right? So rate is equal to minus changes of concentrations of the starting material, because it is if A is the starting material, then definitely it is a minus with respect to T. So del concentration of A divided by del T equal to K is the rate constant multiplied by concentration of reactant. So if reactant is zero order, then it is equal to K, and then basically you can derive. I think you have practiced all the derivations in the beginning of this course, right? So there is one experiment in CMP 100. I think you people has not done any CMP 100, but yeah, you are the second year. So last year, because of the COVID, there was no practical. So one of the experiment is based on the kinetics. That is the acid catalyzed hydrolysis of ethyl acetate. Okay, and in December, I think either first batch or second batch, I don't know. Okay, that we are deciding, probably the first 20 batch, 1 to 20. We have not decided yet. So the CMP practical will be held in December winter vacation. So you have to come here. So there you will practically do how to determine the rate law of a particular reaction, that is the acid catalyzed hydrolysis of ethyl acetate. So there are various techniques. So whenever you will do an experiment, so what you need to do, basically you need to calculate the changes of concentrations of the reactant or changes the concentrations of the product, because reactant is converting to product with respect to time. So time is very important. So you need to measure the time accurately with the measurement of the concentrations of the starting material or product accurately. Accuracy is very important here whenever you will measure the rate law by experiment. So in the CMP 100, the experiment you will be doing probably in the next summer or this December, you will use titration. So you will use titration. So if the starting material product is suppose acid, so you will be using you will be doing the experiment of hydrolysis of ethyl acetate. So ethyl acetate will convert to ethanol, methanol and acetic acid. So if the acid is the product, then you can easily determine the concentration of the acid by titration using base, right? If the base is producing, then definitely it will be also be an easy technique to titrate the to titrate the formation of the base. What is the concentration of base using acid? Reverse way. If the product is difficult to analyze by titration, then the several spectroscopic method we can also use. For example, proton NMR or NMR, nuclear magnetic resonance, or UV visual spectroscopy or gas chromatography, that is also routinely we use to run kinetics. So there are several instrumental techniques we can use to know what is the concentrations of the product or starting material with respect to the time. Okay, I think I forgot to turn on the video. Oh, no, someone turned it on. Okay, good. So experiment you will be doing either in summer or in the winter. So here is one of the examples of where that is the decompositions of nitrous oxide. Nitrous oxide on a surface of platinum to convert to nitrogen and oxygen. Actually, that is the reason why platinum is used in catalytic converter. So every car has a catalytic converter where the exhaust comes after the burning the gas fuels or petrol. So there are platinum, rhodium, ruthenium catalysts are there. So what platinum does, some of the nitrogen during the combustion chamber, it produces nitrous oxide as well as nitric oxide. So platinum decomposes the nitrous oxide into nitrogen and oxygen. Okay, this is a practical catalyst. This catalyst exists in every car. Okay, in the catalytic converter. So this is the zero order reaction, zero order with respect to the starting material, that is the N2O. So rate is minus half concentration of N2O divided by time because it's starting material, and you can see that 2N2O is converted to 2N2 plus O2, so that's why it is half, that you know in Shashank Dev's class. So I'm not going to tell in details. So one of the techniques to know that what is the nature of the transition state, we will come in details later. You can first things you need to do that. The first experiment that you need to do that is the find the rate law. Find the rate law. Okay. Sorry. Okay, the second one is the first order reaction. So as you know, that rate is equal to minus concentrations of starting material divided by the changes of time. Okay, changes of concentration of starting material divided by changes of time equal to K into the first order with respect to the concentration of A. A is the starting material. Okay, and I hope you have done all the equations, right? So at the end, after the derivations, you will get ln base E concentration of A starting material equal to ln concentration of A0 minus KT. So what here also what you need to do, basically you need to determine the concentration of starting material, that is the A, with respect to time. Now if you plot a simple concentration versus time, then since it is the first order with respect to concentration of starting material, so concentration of starting material decreases over time. Not only for that, this is the first order, so you will get a curved line, unlike the zero order kinetics. If it is a zero order, it will be a straight line because slope will be the same. Okay, but here this is a kind of exponential slope, exponential plot. Okay, but if you just plot ln concentrations of starting material versus time, so y equal to mx minus c, so you will get a straight line, and whatever the slope you will get, that is the minus k. So from the slope you will get the rate constant, that is k, easily. So all the kinetic experiment, what you need to do is you need to determine the concentration of starting material or product reverse way. If it is a product, then it will be plus, with respect to time and plot in Excel or Origin or by manual, because in CMP 100, okay, you will be provided a graph paper. Okay, not you cannot plot in Excel or Origin. So if you in a graph paper, if you just fit with ln concentration versus time, and if you find that it is a straight line, then this is definitely a first order kinetics, first order with respect to the starting material, right? So this is one of the examples of a first order reaction that is called SN1 type of reaction. You may have learned in CML 100 last year in organic section. So what is SN1 reaction? So this is the tertiary butyl bromide. It reacts with water to give the T-butanol plus Br minus bromide plus H3O plus. This is the balanced chemical equation. Okay, so this is basically the simple hydrolysis of T-butyl bromide. Hydrolysis to give the corresponding T-butanol. So these reactions happen at room temperature. If you just take T-butyl bromide and water, you shake, okay, you will get within half an hour you will get T-butanol. These reactions are very efficient at room temperature. Even you need to heat, you need to just shake or stir. So what is the mechanism? Is the first step is the formation of a carbocation. So this is a multi-step reaction. The first step, I will come in details what are the other possible pathway. So now we are discussing in a simple way that first step give you the answer. What is the first step? First step is producing a carbocation intermediate or transition state. So what is happening here? You can see that the first step is a transition state. So first step is it is forming a transition state. So what is happening here? You can see the one of the carbon, that this carbon and bromine atom, it is getting elongated. Water is not coming here. It is elongated and there is a charge separation, del plus and del minus. So this is the same molecule. This is the same molecule. Only one of the bond is getting elongated, and that's why it is higher in energy, and this is a kind of transition state. And after that, carbon and bromine bond is getting cleaved to form a ion pair intermediate. Ion pair, this is the cation, and definitely you have a bromide anion. Those are called ion pair. But forget about the anion. So basically we are forming a carbocation, the carbon, right? Carbocation intermediate. After the carbocation intermediate is formed, then water comes and it react with the positively charged carbocation and give the product, right? And this Br minus is liberated out. Clear? So what you need to do, so to understand that first you need to determine what is the red law. You don't know, suppose this is a possible pathway. So which step is the rate limiting step or slowest step? There are two steps. First is the formation of carbocation and second step is the attacking of the water to the carbocation to give the T-butanol. So there are two steps. Basically it is the two-step reaction. You don't know the first step is the slowest or second step is the slower than first step. So what you need to do, the simplest things, always run the kinetics and determine the rate law. So basically you need to determine for any spectroscopic method, or if you find that the starting material or product, you can be determine its concentration by titrations, go ahead. Otherwise you can determine by other spectroscopic method, as I told, like gas chromatography or NMR spectroscopy, to determine the concentration, changes of concentrations of the starting material or product with respect to time. So if you find it, then you can see that rate is first order with respect to the starting material, that is t-butyl bromide, and it is zero order with respect to water concentration. This is the concentration. So this is the rate law. A is the rate constant. So that indicates that whatever the slow step or whatever the transition state which is associated with the rate determining step, it doesn't matter it is the highest energy or lower energy, as I told before. But whatever the rate limiting step, in the transition state of the rate limiting step, t-butyl bromide is involved, not water. Not water. Only t-butyl bromide is involved in the step having the highest barrier. So where the t-butyl bromide is involved? It is involved in the first step. Okay. Second step also t-butyl bromide is not involved because the second step only carbocation is here. There is no t-butyl bromide in the second step. In the second step water is there. So this is the second step. This is the first step. Right. So in the first step only the starting material is involved. In the second step water is involved, but water is zero order. So that indicates that first step is the rate determining step having the highest barrier. So if you plot it, the energy profile diagram, then definitely the highest barrier you will see in the first step, that is the formation of carbocation compared to the second step. Okay. All right. So the rate law can easily tell that in the transition state of the rate limiting step here, what kind of molecules are involved? If water is involved, then definitely second step is the rate limiting step or rate determining step. But it is showing that t-butyl bromide is involved in the rate determining step. So the first step is associated with the higher barrier compared to the second step. So this is the energy profile diagram for potential energy versus reaction coordinate in a SN1 type of reaction. This is called SN1. Okay, SN1. 1 means this is the one molecule is involved. Now 2 means bimolecular. We will come later. If you know that is fine, but with kinetics we will discuss more with examples. Okay, any questions?
Sir, here transition state when converts to intermediate, won't that be considered also another step?
No. So transition state is this. Have you seen my writing? So this is the transition state where the carbon bromine bond is being broken. Transition state is continuous process. So continuous means it is the undergoing. It is not completely broken. So how it will be broke? Definitely carbon and bromine bond will get elongate, right? And then ultimately it will break. So this break, after the breaking, this intermediate is forming. So here is the intermediate, as arrows are shown here. Is that answer your question?
Yes.
Yeah. How there will be another one step. Transition state, bond is being broken, not broken, being going on. Okay. So you can see this is the highest in energy. Then here you can see the bromine bond is broken again and again, and once then it is forming the ion pair. And when it is forming the ion pair, it is lower in energy. Okay. And form a intermediate. Any questions? Any more? Any stupid question? No, that's fine. Okay, if it's not, then let's go. I think second order next. So I hope it is very helpful that at least from the rate law, this is the first experiment you need to do always. The what is the rate law? you can get an idea, or you can tell that what is the rate limiting step, means which step is associated with the highest barrier among other steps in a multi-step reaction. If it's single step, that is not a problem, but if it's a multi-step, then a majority of the reactions are multi-steps. Okay, and you can also get an idea what is the possible structure or nature of the transition state in the rate limiting step. So what is a possible transition state? That might be a carbon bromine bond is being broken and getting a charge separation, right? So more charge is forming on the carbon center. But as I told, one experiment is not enough. You have to do multiple other different kind of experiments to establish what is the nature of this transition state. Rate law cannot tell whether there is a charge separation is going or not. Can it tell? No. I am telling maybe it is possible. We can speculate. But rate law cannot tell that whether charge separation is going on, a carbon bromine bond is getting elongated or not. It cannot tell. We have to rely on other methods that I will come later. Okay, so what kind of experiments you can tell to determine whether any charge separation is going on in the transition state or not. Okay, rate law cannot tell. Rate law can only tell what kind of molecules or how many molecules or what type of molecules. Okay, there are two starting metal. Which starting material molecules are involved in the rate determining step? That's it. Right? Okay, second order reactions that you know that rate is second order with respect to the starting material. If the starting material is one kind like A, so if you after the derivations, right, what you will get? If you get a equations 1 by concentration of A equal to 1 by concentration of A0 plus KT. So basically, if you plot 1 by concentration of A versus T, then you will get a straight line, positive slope, definitely, right? And from the slope, you can get the rate constant. And if you just plot the concentration of starting material versus time, then you will see a similar plot of first order. But this is second order, so your initial slope will be much more higher. Okay, because the disappearance of the starting material will be much more faster compared to the first order reaction. So if you determine the changes of concentration or concentration of starting material A at different time, then if you plot concentration of A versus time, and if it is coming a straight line, negative slope, then that is zero order. If you do ln concentration of A versus time, then if you get the straight line, that means that is the first order with respect to A. But if it is not that, then if you plot it 1 by concentration of A with respect to time, then if you get a straight line with positive slope, that means the reaction is second order with respect to the starting material A, that you know that, right? So I'm going to tell two examples. The first one is the Diels order reaction. You may know from your high school or CML 100 organic. Okay. So this is called Diels order reaction or 4+2 cycloaddition. So you can see this is a pentadienone, same molecule. This is one molecule, this is one dot, because this is same. What is going on here? You have alkene bond, and here is one of the alkene bond. This is called 4+2 cycloaddition, and it is giving a dimer. Okay, dimer. If you determine the rate, so what is the concentration? If you just determine the concentration of the product, or concentrations of disappearance, concentration of starting material with respect to time, then you will find that rate is actually second order with respect to monomer die-in. Okay, monomer die-in. So what does it mean? This is a very interesting thing. Okay. So rate is second order with respect to die-in. So that is very interesting. So what does it mean? That means that whatever the transition state, we don't know this is a single step or multi-step, but whatever it is, suppose this is a single step, starting material, and this is given product, and this is the die-in, suppose D E. So whatever the rate limiting step or rate determining step it has, Rate law is telling that first of all die-in is involved and how many molecule of die-in is involved. So there are only one type of starting material is there. There are not two starting material is there. Only one type of starting material is there. That is the die-in. This one, right? One. So red law is indicating that in the transition state or rate determining step, two molecule of die-in is involved, and that is very obvious. This is a 4+2 cycloaddition. Definitely this dimer will form. How the dimer will form? Basically by the reactions of two monomer. It's very simple. And that is also consistent with our rate law. Rate law is telling this is the second order with respect to the die-in. So two molecule die-in need to come close to each other and undergo reactions in the transition state. So whatever the transition state it goes, we don't know what is going on in the transition state, but red law is in telling we don't know actually what is the nature of the transition state. Okay, you know that, okay, this is going like this way, arrow, you are showing arrow, okay, like 4+2 is cycloadditions, this is going on. That you can speculate, okay, this is going on, but red law is telling what is the structure of the transition state, that we don't know, but red law is telling that at least two monomer is involved in the transition state. Clear? Two monomer or two molecule of die-in is involved in the transition state. So you need to do additional experiments to know what is the nature of the transition state. Even if from the red law, if you know that two molecules are coming to each other in the transition state, then you can speculate and draw a structure. Okay, this is might be the possible transition state. Okay, that is the main thing. The second reactions is the SN2 reactions. SN1 versus SN2, I told SN2 that is means nucleophilic substitution or substituted nucleophile. Two indicates that it is bimolecular. Two molecule is involved in the transition state. So what is the reaction? So reaction is basically this is the benzyl, this is the ethyl chloride CH3CH2Cl reactions with bromide. So on the CCl bond is getting clipped and CBr bond is forming to give the ethyl bromide. So basically this reaction is ethyl chloride plus Br minus to giving the ethyl bromide plus Cl minus. Okay, plus Cl minus. So this is called nucleophilic substitution. So you can see that these substitutions of chlorine bond with bromine, not chlorine bond, chlorine atom with bromine. So ethyl chloride is converting to ethyl bromide. Okay, clear? So here, unlike the SN1 type of reaction, SN1 type of reaction is similar. where water was there. And you know that the carbocation is the intermediate. And only the starting material, that is that similar to like bromide or chloride, is involved in the rate determining step. But here Red law is telling in a different thing. The rate is telling this is the first order with respect to ethyl chloride, and there is another one reagent, that is the bromide. It is also the first order with respect to the bromide. So what the rate law indicates that whatever the rate determining step, if it is a single step, then doesn't matter, there is only one transition state. But if it is multiple step, there are multiple transition state. And but if there is multiple transition state, then you need to find which one is the rate determining step, means it has the highest barrier. So Red law is telling for these cases that whatever the transition state associated in the rate limiting step, they are both one molecule of so ethyl chloride, and one anion of bromide, one bromide anion is involved. So in the transition state of the rate limiting step, one molecule of starting material, that is ethyl chloride, is involved, as well as one bromide anion is involved. So both are involved in the transition state. You don't know what is the nature of the transition state, what might be the possible structure, but Red law is telling that how many and what type of starting material molecules are involved in the rate determining step. That's it. But that's the first point and most important point to know the nature of the transition state. So what might be the transition state? So transition state means that bromide is attacking to the carbon and chlorine is leaving. That might be a possible transition state where the both starting material bromide anion and as well as ethyl chloride is involved in the transition state of the rate limiting step or rate determining step. So this is a single step reaction. This is a single step reaction. And what is the transition state? This is the transition state. Compared to that, if it is SN1 reactions, it is a two-step reaction. It is a two-step reaction, right? Here, if it is SN1, then water should be involved in the transition state. But here water is zero order in SN1 type of reactions. That is also indicates that this is the two-step reactions, and first step is the rate determining. But in SN2 type reactions, it is telling that it is likely a single step reaction, and in the transition state both static material is involved. So what might be the transition state? It looks like a possible, based on the symmetry, a trigonal pyramidal kind of structure where carbon is 5 coordinated, where the CBr bond is forming and CCl bond is cleaving. It is not completed process, it is going on. It is going on. Okay, it is going on. Okay, so question? Question?
Yes.
Is it clear or not?
Yes.
You can see that how Red law is really helpful to understand what is the nature of the transition state. Any questions? No? Okay. So there are two examples, another one examples that NO2 to NO plus O2. This is catalytic process, and also HI, hydroiodic acid, decomposition of HI2, H2 and I2. Those are also second order reaction. Those are also second order reaction. Okay. So Red law is really helpful to determine the rate limiting step. So here is the couple of examples. It's the same table I will show again and again, but here I am going to discuss one by one with more examples. Okay, but how can you determine what is going on in the transition state of the rate limiting step, okay, or to in the rate determining step is by rate law. The first one is acid catalyzed hydrolysis of ethyl acetate. Acid catalyzed hydrolysis of ethyl acetate in water, that I was telling you 2 slides before. This experiment is in the syllabus of CMP 100 that you will be doing later this year or next year summer. Okay, so what is this? This is the ethyl acetate. You are using water, using a little bit of acid that acts as a catalyst. So ethyl acetate plus water, it is forming acetic acid plus ethanol. So if you determine the rate law, then rate is actually first order with respect to ethyl acetate and first order with respect to water. So what does it mean? What is going on? What is the possible structure in transition state or rate determining step? If it is the single step, then the rate determining step is the single transition state, as I told. If it is multiple step, then rate law indicates which step is the rate determining step with highest barrier, right? So in the rate determining step, it is involved. It indicates that water and ethyl acetate both are involved. So attacking of the water on the carbonyl carbon of the ethyl acetate is the rate determining step. So this is the rate determining step, transition state in the rate limiting step. This is going on in the transition state. Okay, rate law can easily tell. If it is zero order, then this is not. So water should not be involved. Similar to like SN1 type of reaction. So maybe there is something else will go, but at least this is not the rate determining step. If it is a zero order with respect to water. Clear? Okay. Is it clear? Any questions? We will discuss more what is the mechanism, but I am now focusing only about the rate determining step. Any questions? Okay. So second reaction is the acid catalyzed ring opening of ethylene oxide in water. So you don't know what is the rate determining step. So you basically do the kinetics and find the rate law. Rate law is telling this is first order with respect to ethylene oxide. This is the ethylene oxide, this part. This is also acid catalyzed. Okay, so here is the acid. This proton is binding here. Okay, and water is also first order. So that means attacking of the water on the carbon and ring opening is happening in the rate determining step. So in the rate determining step, ethylene oxide is involved and water is also involved. Rate law is telling both are involved. So it is likely that water is attacking on one of the carbon atom of ethylene oxide and ring opening is taking place in the transition state of a turnover limiting step. Okay, clear? Here is more examples. I will send you the slide. Look at. Okay, let's do this fourth one. This is quite interesting. This is same thing. SN2. This is another one examples of SN2 type of reaction. So basically the reactions of pyridine with, you can see the displacement of iodine from methyl iodide by pyridine. Okay. So what is happening? The pyridine plus methyl iodide is giving to form the N-methyl pyridine plus I minus. So this is the kind of SN2 type of reactions where so rate law is telling that this is first order with respect to the pyridine, first order with respect to the methyl iodide, right? Okay. So that indicates that whatever the rate limiting step it has, both molecules are involved. So this indicates that this is the kind of SN2 type of reactions where this is attacking the pyridine, nitrogen is attacking here on the nitrogen and iodide is leaving. See the arrow. in the transition state, similar to SN2 type of reaction. It is a concerted process. That's why both are involved in the rate limiting step or rate determining step. Is it clear? Clear?
Yes, sir.
Yes, sir.
Good. If it's not clear, please tell. Don't tell yes, sir. I will repeat again and again, 100 times, no problem. Okay. But this is similar case. Okay, the fifth one, you can see this is a kind of, I think, same example probably, SN1 type of reaction. This is the hydrolysis of T-butyl chloride in water. So if you just take T-butyl chloride plus water, okay, plus water, what hydrolysis? So what will be the product? You are getting T-butanol. I think same we discussed before. So this the rate is first order with respect to the T-butyl chloride, but zero order with respect to water. So this is not a concerted process that water is attacking like this. So this is a similar type of SN1 reactions. So what is the possible pathway? What is the nature of the transition state in the rate limiting step? That is the formation of carbocation. Yeah. Right, then water will come. The same thing we discussed before. So you can see that how the rate law is so powerful to determine what is the nature of the transition state or rate determining step. Okay, it's a very powerful method, the rate law, the kinetics. Anyway, in the kinetics is the first thing, but rate law is the first thing. Experimental first experiment to understand the kinetics of a reaction. Okay, there are other steps that I will tell later. Okay, future class. So here the hydrolysis of T-butyl chloride. The rate law is telling that water is not involved in the rate determining step. So the first step is the rate determining step where carbocation is forming. But whether carbocation is forming or not, that rate law cannot tell. Rate law cannot tell. You need other methods. I will tell later. Okay, it is suggesting probably the plus charge is forming, carbocation is forming as the intermediate because water is not involved. At least it is not a concerted process like SN2 type. Okay, so it might be plus charge is forming and forming a carbocation, might be. But it is giving a hint because water is not involved here. Okay. Same thing here. What about the so you can predict also what is the rate law if you know what is the nature of what is the transition state or rate limiting step. So what is the number 6? What will be the rate law? What do you think? This is the conjugated addition reactions. So you may think that this will be the first order with respect to the pH S minus, right? So this is the phenyl sulfide and this is the alpha beta unsaturated ketone. This is conjugated addition. Okay, so it should be the first order with respect to both. The last one is the peroxide homolysis. Peroxide homolysis. So 2 gives radical. Okay, to give the radical. So this is just cleaving here. So what meant by rate law? So rate law should be only the first order with respect to the peroxide. Okay, peroxide. So you can see that the simple determinations of the rate law can tell you which step is the rate limiting step, and not only for that, it can give a hint what is going on in the transition state of the rate determining step. Even though you cannot confirm that what is the possible structure, but it can give a hint, right?
Yes.
Okay, I think I'm getting a little late. Next time I will teach a little faster. But anyway, it doesn't matter. The rate law. So I thought I will finish Hemant's postulate. There is postulate, but I will teach tomorrow. Hemant's postulate and next is the activation parameter. That I will try to finish tomorrow. Okay. Any questions? Questions? Any questions? Any questions? Otherwise, I will stop. And the Hemant postulate and activation parameter we will discuss tomorrow. Questions? No? Is it okay? I'm teaching very fast, slow. I'm teaching very slow. Is it understandable?
Yes, sir.
Hello. Okay.
Yes.
Yeah. If I teach faster, okay, slow is not a problem. I like to teach slowly. Okay. The thing is that your understanding is the most important thing. The way I want to teach that, okay, you can at least after finishing the course, you can remember that, okay, how to determine the nature of the transition state. Okay, so I'm trying to teach in a pictorial way, no equations. Okay, equations, whatever you have done, I think that's enough for your for the first half of this course by Professor Sandeep. Okay, because I know that equations you will forget. Even I forgot also. I don't care. Okay, I want we need to know what is going on, the pictorial, okay, the picture basically, okay, the pictorial understanding, so that you can easily remember for a long time, even if you finish this course, after the finishing this course, even if you maybe after your graduations at the end of your 4th year, if you just remember a little bit, that's enough. At least how to determine the nature of the transition state. Okay, so I'm trying to teach you with more examples in a pictorial way. Okay, no more equation. Okay, then I am leaving. Okay, so tomorrow at 12 o'clock, I will teach first Hemant postulate and then activation parameters. All are very interesting methods to determine the nature of the transition state. Okay, and slides at by 4 or 5 o'clock, I need to modify a couple of slides. Then I will upload in Moodle. Please download. Okay, by 5 o'clock. Okay, bye bye.
Thank you. Thank you, sir. Thank you.
Thank you. Thank you.